I hope you can hear me. The owl is a little bit away from us, but hopefully you can hear us. So we, the four of us, worked together on flow cytometry. Our data set was a hot cruise just north of Hawaii, using the seaflow continuous flow cytometer. The top panel is kind of what the data ends up looking like with the 3 different fluorescence parameters that we are measuring. And the goal is to cluster groups of particles into populations. There's beads plus 4 different phytoplankton populations that we're interested in. This bottom panel was done by me by hand. And the idea is to go hands-free and using machine learning or other type of algorithms. And we kind of threw the kitchen sink at it, where each of us did something a little bit different. Charlene and I looked at hierarchical clustering, and then doing kind of more creative and deeper cutting using dynamic tree cut. And so this dendrogram is drawn from every single particle in 1 hour, and clustered using distances that we calculated. And these color bars that you see are a variety of different algorithms or parameters within dynamic tree cut, which is a package in R. The bottom one is if I just cut straight across to get 10 branches. And you can see there's a very large blob that is mostly Prochlorococcus with a few other things. And in the end, that's actually the one that worked best, at least for this configuration. The GIF that you see in the bottom are the identified particles, where it's able to get beads and Crocosphaera, as well as Symphycoccus, and the pro kind of ends up with the noise.
Yeah, so I started out similar, just trying lots of different methods to see what worked. So, like I said at the top, I tried Gaussian and one called Birch and one called DB scan. And I wasn't having much luck, mainly because if you see on the GIF, the bottom left corner is the bright purple blob is really dense particles, like there's thousands compared to what there is at the top right. So like choosing a specific number of clusters to look for didn't really work. So I tried some other ideas. I tried hierarchical clustering, which is the diagram on the top right, which worked better, but it's still having problems over on the bottom left, as you can see. I tried applying grids to all the data and then doing it, but that didn't work too well either. And then what did have some success was using the density, which Jinting helps with, and he'll talk about later, to identify the most dense part, which is this Prochlorococcus down at the bottom left. Removing that and then clustering everything out separately. And this is what you see on the GIF. I've removed like the purple blob, done everything else, and then put it back in, which works quite well. And then this is also over a 24-hour period. So to get that to stay the same colors throughout each time period was also a bit of a challenge. But using GMM, the Gaussian one seemed to work the best for that, as you can see. And I'll pass over to Jinting.
So I first used the K-means and the agglomerative method to do the clustering assignment. And the agglomerative method is just a kind of the hierarchical clustering. And they have similar results, as you can see. And then I tried the Gaussian mixture model, and I did some improvements. So first, I reduced the class imbalance. As you can see, the left bottom corner is less dense than what it was compared to the K-means and agglomerative method. And then I used some predetermined initial centers. So what I did was that I substituted the cluster centers so that you can see the top right corner. There are 2 clusters at the top right corner, but there is only 1 cluster by the K-means and agglomerative method. So that was better. And then I used the probability method. So the GMM, which is Gaussian mixture model, has a method called compute probability, which is to compute the probability of each point falling into its cluster. So what we can do is we can set a threshold value So that if the probability of a point falling in its cluster is less than that threshold value, we can like do something like what I did here is to color it as black. And the bottom line is just the density loss over the time hours of data.
And that's all for us.
Fantastic.